So my name is Levente Csikor, and I'm here with my colleague Gabor Retvari, who is sitting there at that round table. And here I'm going to talk about some corner cases of the Megaflow caches. And this was a joint work with around the globe from contributing by Stefan Smith from University of Vienna, Dimitris Pezaros from the University of Glasgow, and Christiana Stevie Rodenberg from the University of Campinas. So let's start. So first of all, what was the main aim of vSwitch in the beginning? As far as I know, it was to meet the needs of the open source networking community, to just provide a feature-rich OpenFlow switch, to manage all the underlying network-related stuffs beyond the KVM virtual machines. And so far, due to its evolution, it became the de facto standard of OpenFlow software switch. It became the most popular backend in OpenStack, and it also started to gain a foothold in serverless environments. And the reason of this success is actually because it's being a masterpiece, and it always catched up with the industrial needs, and faster, and even faster without sacrificing its main advantages, the high programmability and the generality. So it's fast. So why is it so fast? So it introduces slow pass and fast pass separation. So if we have a flow table here with a simple flow rule, the flow table actually looks like we have an ordered set of wildcard rules, as you can see. So we can wildcard some bits if we want to match on some specific headers. It also contains yet a set of headers that we can filter on. And it's got a set of packet processing primitives. So this is how the flow table looks like, and this is managed by the OVS vSwitch daemon in the user space. And of course, in the user space, these flow rules can overlap. So there are priorities if the first rule it has higher priority as the last rule, or you can also define priorities on your own. And to fasten this packet classification itself, only the first packet is subjected to this full-blown packet processing in the flow table in the slow pass. And once we found the matching entry in the flow table, then all the subsequent packets later can just pass through the kernel. And this is why it can be fast. So let's talk about now the flow caches, because everything which is going to be said by myself here is concentrating on the Megaflow cache itself. So I did a fancy animation here. I hope you're going to like it. So here we have the exact match cache, and once a packet is coming in from a source IP address 10.0.0.1, there's nothing in the exact match cache at the moment, so it's going to be a cache miss event, then it's going to be passed on the top to the Megaflow cache as well, where there is also empty, so there is no entry to match on. So finally it will send upwards to the user space where the flow table is sitting, and then it's going to be a match for this packet with the first flow rule, which means that according to the actions it's specified, it's going to be sent out at the right port, and it's going to update the cache itself. So we can see here that the Megaflow cache actually has some bits that can be wildcarded. This is actually one of the biggest improvements in vSwitch, as far as I know, in terms of performance, to have this arbitrary bitwise wildcarding in the fast pass. And we also have the Megaflow cache, which is actually the microflow cache, which is a pair transport cache. It hashes everything. So even if just one little bit is changed in the incoming packet's header, it's going to spawn a new entry in the exact match cache. So if a new packet is coming in from the same source IP range, then of course it will be there will be a cache miss in the exact match cache, because there is no such a specific hash that can be matched on, and it's sent upwards to the Megaflow cache, where finally we have an entry for this according to the wildcarded bits. So this packet shouldn't be sent upwards to the flow table and the slow pass. So accordingly, we can send that packet out to the right direction, and we also update the microflow cache as well with the new entry. And then, of course, a third packet comes in, which has no entry again in the caches. Then that will also go upwards to the flow table. There is also no entry in the Megaflow cache. So as I said, it's going upwards again. The new flow rule and the matching entry will be found in the flow table, and accordingly, again, the caches are going to be updated. So as you can see, there is only two entries in the Megaflow cache for handling 3 packets. And of course, there are 3 entries in the exact match cache to handle these 3 packets. Let's go for, so let's get a deeper insight into Megaflow cache. So the data structure itself, it's based on tuple space search, which is always really difficult to implement in software, so it's a really complex task. What tuple space search, in a sense, means that entries that are matching on the same header fields are actually collected into a hash, where all the masked packets can be found fast. And to reduce the complexity, the vSwitch daemon, or in other terms, the slow pass, are actually tries to make them, not tries, but ensures that all the entries in the Megaflow cache will be non-overlapping, which means that the masks and the associated hashes are searched or can be searched sequentially. And since they are non-overlapping, once we found a matching entry, we can decide whether to send the packet to an output port or just drop it, but we don't need to search the whole problem space. So of course, since it's a linear search, it can be costly if we have a lot of masks in this Megaflow cache. So let's see an ACL example. It's going to be around a hypothetical 3-bit protocol. So forgive me about the example, but it's really good to show it. But of course, it doesn't make any sense. We don't have any 3-bit protocol. So assume that we have a flow table here, which matches on 0, 0, 0 on this hypothetical protocol, and everything else which is coming into the switch should be dropped. Okay, so we get 2 overlapping flow rules. The Megaflow cache needs to distinguish. So in the Megaflow cache, we need to distinguish among all possible packets that can have this 3-bit protocol. So now here we have a cube, which actually tries to represent all the possible 3-bit solutions or all the possible 3-bit set in a specific packets. And here we have the Megaflow cache, which is at the beginning is empty. So for the one flow rule, for the allo rule, so this is the allo rule. Okay, so this is the allo rule here. For the allo rule, we need to have an exact match even in the Megaflow cache entry, because that's the only packet that we can let into the system, and everything else should be filtered out. So there is only one entry at the beginning in the Megaflow cache with no bits wildcarded. And to cover the whole problem space, the Megaflow, so we need to somehow cover the rest of the corners of the cube, right? So if we would have an exact match on all of the corners, then it would result in the same exact match cache that we already have one layer below. So let's wildcard some bits. So let's see how it would look like if we try to cover the rest of the problem field. So we can also define a wildcarded key mask entry in the Megaflow cache like this to cover that part of the cube. We can also have a coverage like that. And the top of the cube can be covered like this. So you can see that we have like 5 Megaflow cache entries to cover everything in this 3-bit protocol space. Of course, there are more than one solution. So I can wildcard, I wouldn't say arbitrarily, but there's always more than one solution. And what we found out that OVS actually tries to wildcard most of the bits it can, which means that, for instance, in this case, it probably ends up something like this. So it will realize after a specific runtime that it can reduce the number of entries in the cache. So you can see that now we can cover the 4 bits on the top with only just 1 entry. So and we reduce the number of entries from 5 to 4. So there's some CRM. So we have a CRM that for an ACL on the W-bit header field, compromising just a single exact match rule for letting one kind of specific packet into the network and just drop everything else. Actually, we cannot have any Megaflow cache representation that can achieve better than ordo k time complexity or with ordo k 2 on the power of w divided by k, where actually k here in this sense tries to balance between the time complexity and the space complexity. And it turned out that OVS tends to lean towards k equals to w, which means it tries to reduce the memory footprint, so to have the less amount of entries in the Megaflow cache instead of being so fast. And the thing how we get to this is just open the classifier header file from the source code. where actually the developer says that, yeah, using 0 bits and masking out some part of the header, it's a really good thing, but they don't really know. So at the moment, there's no rule of thumb how to make this. So they also use various approximations to make this coverage in the cube that I showed before. So let's see how this Megaflow cache actually can grow. So we just saw that even for a simple flow rule on 3 bits can actually spawn 3 masks and 4 entries in total. So just let's see what happens for 8 bits. So for instance, if we try to filter on a source IP with a /8 prefix, here it is actually 10.0.0.0/8, and we also have a catch-all drop rule in the bottom. Then we can finally end up having like 8 different masks in the Megaflow cache, which is also 9 entries in the cache. So you can see here that these are the IP address ranges that actually covering the rest of the whole protocol space in terms of these 8 bits. We also should note that in order to have these entries in the Megaflow cache, you need to have the corresponding packets that are coming into the system, because a new entry in the cache is only spawned when a packet came in. So we assume here that the packets are actually entering our system. And what you cannot see here, maybe on the bottom, that it means that if you have a one flow rule on W bit, then you can actually reach a W bit plus 1 number of Megaflow cache entries in all cases. So let's see again just this, how it can grow further. So yeah, so this is an evil plan. So how can I actually make this Megaflow cache representation or materialization in my data path? So I have the same flow table as we had before. And I just received a Voodoo packet generator from Santa, which means that if I know the flow table, and I put it into my system, and I also know the details that I just showed you before, so how the Megaflow cache building bricks are actually handled during the process, I can actually squeeze this into a packet processor, and I just wait a couple of seconds, and this packet generator will actually tell me what are the packets that are actually going to spawn all those Megaflow cache entries. And according to this, I can just feed these Christmas packets into the switch, which eventually will result in having those specific number of entries in the Megaflow cache. So I don't need to actually generate all possible packets that you can ever imagine if I know how these bits and wildcards are handled in the system itself. So let's do the math. So if we have 3-bit protocols, we can see 3 masks and 4 entries. For 8 bits, we got 8 masks. For 30 bits, we got 32 masks and 33 entries. And that's only one flow rule on one header field. So it's the corner case of the corner cases, right? So actually, if you want to match on multiple header fields, you finally end up in this typical cross-product problem of having multiple tables, for instance, in the pipeline, which will mean that if I try to match on the TCP port only, that I have 16 bits, so it will represent 16 bits or 16 entries in the Megaflow cache. If I also add a new flow rule, which matches on the IP source address, which has 32 bits, then I finally ended up, if I had the right packet sequence with the Santa's packet crafter, then I can actually reach more than 500 entries, and this is how it actually can be increased. So even with 3 flow rules on 3 different header fields, I can achieve like thousands of Megaflow cache entries. So now I'm going to give a demonstration about this and about some dissemination. So first, when we realized that this disadvantage of the system, we first send a notification to the developers, and BAMFAF, thanks, he acknowledged that that they received it. So and we had a SIGCOMM demonstration about this, without, of course, revealing all the necessary steps to reproduce this stuff. And we have also a more comprehensive work under review at the moment. So now I guess I still have so this is the setup that we are going to use during our demonstration. So it's a synthetic setup using kernel virtual machines. Here, it's really difficult from the mirror part to point to the right way. So we have 2 server nodes, server node 1 and server node 2, each hosting VMs. Here we talk about victim VMs, which are which are just regular VMs that are having pure hyperv traffic between each other. And now we have attackers, but I don't really talk about attackers at the moment. We have attackers who has this packet Santa crafter, or packet crafter from SANA, which can send some bulk traffic into vSwitch. And we have, the servers are connected to a physical 4DG link. And each of the servers have an vSwitch as a hypervisor switch. And this is the flow table what we have here. So what you can see here that the two flow tables on the top is actually just providing the necessary communications for the victim's VMs. So you can see the corresponding IP addresses are there. And now we have only two flow rules. One is matching on a TCP destination, and the other one is matching on the IP source address. We have also destination address here, but in this sense, it doesn't make any sense. It's just there all the time in our flow table. And for our setup, we used a simple hardware, just a Xeon CPU with, you don't see it, it's 64 gigabyte of RAM, so it's not 4G of RAM. And we got the freshest stable Ubuntu, and we had the freshest vSwitch, which was considered as a stable one, and it was installed from the official Ubuntu repository. So let's see how this, so we have a, okay, does it still show something? Okay, maybe. Maybe I refresh it. It was working before, trust me. Okay, I just want to give it a try again. Okay, I close and this is what always happens when you try to do some live demonstration. Okay, I'm actually disconnected from this stuff. Oh no, it's getting back. So I still got a couple of minutes. I will go for the backup slides if it won't work. Okay, it seems it's working. Yeah, okay, it's good. That was the main aim of our demonstration, to show this. So here we have 3 plots. This is just a simple plot about the current CPU load. So all the servers are doing nothing, just running these VMs and getting through the hyperv traffic between the VMs and having the vSwitch itself running as a hypervisor layer. On the second plot, bring this away. On the second plot, we can see the current Megaflow caches at the time. So there are only just a couple because the traffic between the victims' machines are on the top. And you can see here the performance. Let's see what. Yeah, you can see here the performance. Right now, you can see that it's around 8 gigabits per sec. And I still have the flow tables that I showed you before inside the system. So if I generate some packet sequence according to just the TCP destination port 80, with a speed like only 1,000 packets per second, I can show you what happens. So now this kind of packet sequence is in, and you can see that I just generated 20 entries in the Megaflow cache with my right packet sequence, and the performance was actually dropped to almost half of it. And now vSwitch is running in kernel space with only consuming 1 core at the time. That was another interesting part of how we are measuring. So let's see what happens if I also try to send some packets on the IP source IP flow rule as well. So I kill here it's okay. Yeah, that's it. Okay. Come on, come on. Yeah, 64. Yeah, it's a bit slow, but our servers are in Hungary, so sorry about that. So now we are sending, as I said, just another packet sequence, which also have these source IP addresses. And what you can see is actually that the number of cache entries are skyrocketed to just to 500 and even more. And the already on victim traffic, I would say victim traffic, so the performance just dropped down close to 0. And the good thing, I wouldn't say good, but the thing is that it's if we consider this yellow line as an attacker, it's not really an attack because the number of packets and the speed that how we are sending these packets into the system could be considered as a covered packet sequence because it's really low compared to the actual traffic that the VMs itself are having between each other. So yeah, these were the fallback slides. So just to recap, so this was the original one, and this is when we are on the TCP destination port as well. This is where we are also at the flow rule for the source IP address, and we can even go a bit lower if we introduce another header field, which increases the number of Megaflow cache entries from hundreds to thousands. And just to consider the effects on a broader scale, so all the cloud deployments that are actually using vSwitch, at the moment that it can be a corner case in some cases. So this is just an example measurement done in a Kubernetes, but we also measured similar performance issues with all possible deployments that relies on vSwitch as a hypervisor switch. So and if we are thinking about how we can mitigate this, so we also try to figure out what we can do. So if you increase the number of CPU cores, of course, so if you have more resources that vSwitch can, of course, handle these increased number of Megaflow caches more efficiently, or you might disable the Megaflow cache at all, but we don't know what that will result in actually, because it also fasten the whole packet processing itself. So if you disable it, you might get rid of this kind of issue, but you might have a slower packet performance on the other end. And you can also offload this ACR processing to something else. You can offload vSwitch to some SmartNIC, and you can also enable jumbo frames because here we are talking about per packet performance. So if the packets are of course bigger than the 1500 MTU, then the overall throughput in terms of gigabits per sec will be also a bit better. And of course, you can use this monitoring tool that I just showed you, which tries to, I don't know, raise some alarms when the number of cache entries increase. And of course, we are really open to what do you think about it, how can it be improved, and we are really curious about what the audience can say about this. So thank you, and sorry, I'm still in time, hopefully. So thank you, and I'm happy to answer any question you have.
So let's thank our speaker. And we're running ahead of schedule, so we have plenty of time for questions here.
Excellent talk. This session might have woken up everybody, I guess, in the room. So how do we find out the number of MFC entries? Is there a stat that we can use today, or how did you figure out the number of MFC entries in a given?
So it turned out that, as I showed you on the cube, so it's actually a proper bit position of the ones in the header field. So if you know, so you need to know the binary representation of the bits that you are attacking on it, and you just actually try to shift that bits each time on the left and on the right, and you can finally end up just having 8 or even the number of bits, number of packets. And this is how you can generate this. So just shift the 1 bit in different position, and you will finally end up at this case. Okay. I can talk about this later offline, but I just don't want to.
Sure.
So the OVS dpkittle show command will show the current number of Megaflow masks.
Okay. So that was the question. Sorry, I thought the question was about how we realized to. Okay, thanks.
Your answer was good too. It was just
okay.
So on the, so one of the stats that's available when you run that OVS dpkittle command, I think, is how many masks were looked up before an entry was found. So just for everyone else, that the way that we do this tuple space search is that each mask ends up being its own hash table, and then we run through all of them. And right now, that logic is pretty dumb. Those get those hash tables are placed in the order in which they're created. So we don't do any sort of rebalancing as the traffic is run. Have you looked at, like, if we were a little smarter about about reordering those hash tables, would that help in this situation a bit?
Yeah, actually, we were looking for this because we realized that this kind of degradation of service can only achieved if there are already existing flow rules in the cache. So if there are some flow rules corresponding to the victim traffic in this term, and then the attacker steps into the place, then this kind of attack can be effective. But in the reverse direction, when the attacker is already there, and then steps in the victim, then it doesn't work. We don't know that why. It's probably because the thing that you are telling right now at the moment. So, and we also had some measurements on DPDK based stuff, which tries to prioritize, I guess. I'm not really aware of how it does it, but it has some kind of prioritization. So if there are more packets matching on some of the flow, it will be prioritized and it will be much faster in the cache itself. So that's the current state of our insight about this thing.
Okay, yeah, so it might be worth, maybe we can talk later and look at the...
Yeah, sure.
And then just one other quick question. You had said that it dropped down to single core performance. Do you know why? Was that because you were sending one flow, or like why did it... You said you ran the test and then suddenly it dropped because now it was using one core. I didn't understand why that happened.
So you mean how did we set OpenVSwitch to run on one core only, or?
Well, I thought you were saying that it was running, maybe I misunderstood, but I thought you were saying that the performance was good, and then it sounded like you were implying that it was running across multiple cores, and then when you ran your test, then it dropped down and it was using just a single core.
Yeah, that's true. So the thing is that the latest OpenVSwitch that we downloaded, it was the 9.0.
Yeah.
I don't know how it was managed, but it only consumes one core, even if it is in a kernel space. So by default. And when we had a previous OpenVSwitch version evaluation, like the 2.5, it auto-scales to as many cores as you have in the kernel space. And then we realized that if you can consume more resources, then you can also have a much increased number of entries in the Megaflow cache to handle. So then you won't get this degradation if you have more resources.
Okay, I'm a little confused about that, but we'll only talk about it offline.
Okay, sorry.
Yeah, thank you.
Hello. Interesting talk, thank you. I was wondering if there is an automated way at connection setup on deciding if this entry should be in the exact match cache or the Megaflow cache. How is that decision being made currently?
I'm sorry, I kind of lost the half of it. Can you repeat it a bit louder?
When a connection is set up, how do you decide which table that connection should go to? Should it be part of the Megaflow cache or the exact match cache?
So how do we decide whether the packets will match on the...
No, packets will match after the entries in the table. How do you decide which table to put the entry in?
Okay, so first of all, to do this, you also need to have access for the flow table as well. So normally, like in a cloud, you don't really have an access to the flow tables itself. But if you are defining your own network policies in an OpenStack or in Kubernetes, like if you want to allow some HTTP traffic into your VM, for instance, then even if you are using just the cloud management system, it will finally translate it into some kind of flow rules in the OpenVSwitch if OpenVSwitch is used. So this is how you can put flow rules into the flow table. And since you know the flow rule, as I said, if you know how the flow rule looks like, the flow table looks like, then you can generate the corresponding packet sequence to achieve the same effect that I showed here. I don't know whether I answered your question, but...
Yeah, I understand what you're saying, but I think we should talk offline. Thanks.
Okay.
Any more questions? All right, let's thank our speaker one more time.